Hello students, this is Dr. Rumsey and we're here to start a new section called probability, and the first part will be about probability rules and the second part will be about conditional probability. So our agenda is to learn basic terms and concepts of probability, how to calculate probabilities, and we have 3 rules for that. And we'll deal with some special cases. So these are the kind of problems that can all look different until you start seeing a pattern. You have to do enough problems to see a pattern. And once you see the pattern, then all the problems fit into about 4 different groups. And things get a lot easier at that point. So keep plugging away until you start to see a pattern in the problems. So we'll start with the basic terms. You probably know some of these already. Sample space, S, is the set of all possible outcomes. So you're rolling a die, for example, you could have 1, 2, 3, 4, 5, 6 would be your S if you're rolling a die. And an event is a subset of S. So you're interested usually in some subset of S. So maybe what's the probability that I get an even number? So we would look at the even numbers, 2, 4, 6 in this case, and that's an event. So we could call it the letter A. Other events we call capital B, capital C, capital D, etc. And the probability of an event is the long-term chance, that's important, that it will occur. You really don't know in the short term if something has a probability of 1/2, let's say. You don't know what's going to happen in the short term, but you do know that over a long period of time, half the time you'll get that thing happening and half the time you won't. And you denote probability with a capital P of A is what you say. P of A equals the probability of event A. And that's actually a function, right? It takes the event A and assigns it to a number between 0 and 1. So probability is a function. And we have different types of probabilities. They go right along with what you see in a two-way table. We had marginal distribution before. Now we have marginal probability. We had conditional distribution before. Now we have conditional probability. And we can have joint probabilities just like joint distributions. So for example, the marginal probability would be the probability of just one event, just like one variable before. So if I make a little box here, and I have A and B, P of, I'm sorry, not A and B. I'm going a little too fast here. A and not A, B and not B, kind of creating a two-way table, right? So if you had like a 0.3 here for A and B, that's a joint probability because it's an AND probability. And then you had a joint probability for A and not B. Let's say that was 0.1. Probability of A would be 0.3 plus 0.1 is 0.4. And that would be a marginal probability because guess where it is? Out in the margin. So for example, the percentage of Democrats or the probability of being Democrat is P of D, is how you would say it. In a conditional probability, we have this new notation right here. This is a given. It's telling you what subgroup it is. It's not a fraction, but it kind of acts like a fraction. It's saying what proportion of the A's, out of the A's, belong to B. That's what we were looking for. It's the probability of B happening, knowing that A has already happened. So we say probability of B given A. So that's what that little line means over here, this little pipe. So the percentage of group A that have characteristic B, the percentage of Democrats who are male, percentage of Democrats, that goes in the back, because that's the subgroup. What subgroup you're in usually follows the word of, and that's out of. So you put it in the back like you would a fraction idea. And what do you want the probability of? Male, or a percentage for. The percentage of male Democrats, that sounds a little harder, but it's still male Democrats, so you know they're a Democrat. And what's the probability of male being male, knowing that you're a Democrat? So probability of D given M is very different from probability of M given D. Those are not the same. This says I'm out of the males, who are the Democrats. This says out of the Democrats, who are the males. And we'll use this notation a lot, so you'll get a lot of practice. There's the AND probability, also known as the joint probability. And I was showing you here in the little boxes, A, not A, B, not B, that this, for example, is the AND probability of A and B, which is what we're talking about right there. It's an intersection. Used to be denoted by this. We don't use that notation anymore. We just use the word AND. So you'll see us using this as a description of a joint probability. Then we have an OR probability, which is more encompassing. It's bigger. A or B means you can have A, you can have B, or you can have both. It's a union, if you remember that notation from a while back. So if you did A union B, or A or B, here's A, here's B, it means anybody in A, anybody in B, and anybody in both. So you see they kind of get counted, double counted in there. We'll take care of that in the formulas, but that's the idea. Anybody in A, anybody in B, and anybody in both. That's what A or B means. It means A is good enough or B is good enough. Both would be great. In a two-way table, you can write down your marginal probabilities and your AND probabilities. Those are the two that show up on a two-way table. Marginal probabilities are out here in the margins. 0.3 would be probability of paying cash at the gas station. We're at a gas station. We're paying cash or credit, and we're getting a full tank or a partial tank. So 0.3 would be probability of cash, marginal probability. And then you have 0.7 for the marginal probability for credit. And you see those add up to 1. That's called a marginal probability distribution. It just shows all the possibles and how often they occur. And since they're called probabilities, it's a probability distribution. So this is the cash variable, and it has two probabilities. They sum to 1, of course. And then the how much gas you're getting. Probability of a full tank is 35 if you go down the column, and probability of a partial tank is 65 if you go down the second column, and again that adds up to 100. So the marginal probabilities are out here, And the joint probabilities or the and probabilities are these 4 cells right here. Now, there are times when you don't have everything set up in a nice little two-way table where you can pick off all the probabilities and be done with it. Sometimes you're just given pieces and parts of information and you have to put them together to get the probability you're looking for. And to do that, we have 3 main rules that we can use as tools to help us answer these problems. So the first rule is called the multiplication rule, and it's used to find and probabilities if you don't already have them done on a two-way table. So 2 events A and B, the probability of both events occurring is the and probability. And what that says is you can take P of A times P of B given A. So you're splitting it up into 2 stages. First, you're going to look at the A's, and then out of those guys, out of the A's, you're going to look at the B's. So it's kind of like a tree. Here's A, and here's B. You look at all the A's, and then you look at all the B's that came from A. And that's what this probability is here at the second stage. P of B given A. And this is kind of puts weights on things. It gives more voice to a bigger group. P of A times P of B given A. Now this is on the formula sheet, so you can find that. And the second half of the formula sheet is mostly probability, by the way. So let's look at an example of an and probability. Let's say probability of female is 0.6, probability of male is 0.4, probability of yeses for the females, so that would be out of F, 0.25, probability of yes out of the males is 0.3. And I want out of the whole group what's the probability of female and yes. That's out of the whole group. This is a conditional, so it's out of the females. This is a conditional, it's out of the males. So you know a couple things about the females. You know how many females there are, and what percentage, and you know out of the females what percentage said yes. So then automatically you know what percentage said no, right? It would be 75%. Out of the males, you know there's 40% of them, and you know that of the males, you know 30% of them said yes. So 70% said no. So out of the whole group, what's the probability of female and yes? So you want to put the whole group together. Don't just give me information about the group separately like this. Give me information about the whole group. So what's the probability of female and yes? Well, using the multiplication rule, it would be, you could look at the females first, because we have that probability, P of F. And then given the females, you look at the yeses. So yes out of females. So you pull out the females, then you look for the females. Here is the subgroup and find the y's. So this would be 0.6, what we're given, times 0.25, which is 0.15, if I have that right. Yes. And you could do the same thing for the males. P of male and yes is probability of male times the probability of yes given male. All right, let's look at another problem in part 2 of our discussion. So I will end right here. And today we're talking about part 2 of probability and probability rules. Here's an example. Seeing an ad and making a purchase. 40% of customers saw the ad, and of those, 30% made a purchase. Of those who didn't see the ad, 20% made a purchase. So you're given information about two groups, the ones that saw the ad and the ones that didn't see the ad. And you're wanting to know what percentage of all customers saw the ad and made a purchase. So there's two groups who you're looking at the intersection of, saw the ad and made a purchase. That's our first question. And then we have other questions to answer as well. So first thing you want to do is label what you have. 40% of customers saw the ad. So probability ad is 0.4. And of those who saw the ad, 30% made a purchase. So out of those who saw the ad, so it's out of those who saw the ad, and you put purchase here. So probability of purchase out of those who saw the ad is 0.3. And then it says, of those who didn't see the ad, that's given no ad, purchase given no ad is 20%. And then we also need probability of didn't see the ad to kind of balance everything out. And that's 1 minus the 0.4 we were given, which is 0.6. Looking over here on the left. So what percentage of all customers saw the ad and made a purchase? So you want an and probability. Ad and purchase. And using the multiplication rule, you would say if that's the probability of ad, and then times probability of purchase given ad. So you're looking at the people who saw the ad first, and then out of those people, look who made a purchase. Probability of seeing the ad is 0.4. Probability of purchase out of those who saw the ad is 0.3. So this is 0.12. So that would go in the upper left-hand corner of your two-way table. I can get this to move. Okay. Excuse me there for a minute. So this is 0.3, 0.4, let's look at it again, times 0.3 is 0.12. Now, there's another group. The group that saw the ad, you know, is 40. So you know the upper right cell must be 40 minus 12, which is 28. And then the ones who didn't see the ad, that's got to be 60, right? You don't know the total that made a purchase. You don't know the total that didn't make a purchase, but you know they have to sum to 1. All right, so now we got to do a little work to get another cell in the table figured out. So we'll do probability of didn't see the ad and made a purchase. So that would be the probability of no ad times the probability of purchase given no ad. All right, that's why we needed that extra probability of no ad in the previous slide. That's 1 minus 0.4, which is 0.6. And probability of purchase given no ad is, purchase given no ad is right here, 0.2. So that's times 0.2, and this is another 12. I'll circle these here so we can see them better. And then the last lower right cell would be 0.6 minus 0.12, which is 48. Okay, and then you put those together. You get 24 for the total percentage that made a purchase. You get 76 for the total percentage that did not make a purchase, and they sum to 1. So we use the multiplication rule for the upper left and the lower left corners, and then we use subtraction for the other parts. Suppose instead you had the following report. 24% of the customers made a purchase. 50% of those making a purchase saw the ad. 37% of those not making a purchase saw the ad. So now you know about the people who made it, whether you know about the people who made a purchase and you know about the people who didn't make a purchase. And you want to put those together. What percentage of all customers saw the ad and made a purchase? So you want probability saw the ad and made a purchase. And fill out the table. So you might want to stop the recording here and see if you can do this on your own and then come back. So probability of ad and purchase is probability of purchase, because that's what you're given, times probability of ad given purchase. And the probability of purchase is 24. Probability of ad given purchase is 0.5 that was given to us, and that's 12. If we want to go back and label what we have here, 24% made a purchase. 50% of those who made a purchase saw the ad, so it's ad given purchase. It's given purchase because you know that's what they did. That's the group it's out of, like a fraction. 37% of those not making a purchase saw the ad. So that's probability of saw the ad given no purchase. And the last one you want is you have probability of purchase, but you don't have probability of no purchase, which is 1 minus that. 76, yes, 76. And we'll use those to get the pieces that we need. Okay, so the next probability, didn't see the ad and made a purchase, would be probability of purchase times probability of no ad given purchase, 0.24, and then no ad given that they purchased. Well, what is that probability? No ad given purchased. We have ad given purchase. What's no ad given purchase? Well, those two have to sum to 1. Probability of making a purchase is a given, and you either saw the ad or you didn't. So those have to sum to 1. So one of them is 50 and the other one's 50. So this would be 0.5. And I'll just say it's 1 minus 0.5, which is how we got it. 12. So we're getting the same numbers again. We were just given different information to start with. And then we had, for the ones that made a purchase, we have 24 total. So we know that. They sum to 1, so this has to be 76. And then saw the ad given no purchase times probability of no purchase is the next one. That's how you get probability of saw ad and made no purchase. It's no purchase first. The purchase variable is first, because that's what you're given information about, and then they saw the ad given they did not make a purchase. And the probability of no purchase is 76, and ad given no purchase is 37. Let's go back and find that right here. Ad given no purchase, 37. And that is 28. So now I can sum across the top row, get 40. I know the second row must sum to 60 then to add up to 1. So the one on the lower right corner, you can either say 60 minus 12, or you can say 76 minus 28. Whichever one you do, you're still going to get 48 there. So we got the same table as we had last time, the last example, but before we were given information about the ones that saw the ad and information about the ones that didn't. And now we're given information about people who made a purchase and those that didn't. And then we have our 4 cells. And the 4 cells, and we can make and probabilities and a pie chart out of those if we want to show them as a joint distribution. Here's 48. There's a 12. There's a 12. And then 28. And this is called the and probabilities pie chart, but it's also the joint distribution. Joint and go together. Okay, now make sure that you understand both of those examples before you move forward. And ask questions if you have them. Our next topic is independent events. And we talked about that idea a little bit with two-way tables. Same idea is going to happen here. A and B are independent if they don't affect each other. Like 2 roommates just passing through in the apartment, whether one's there does not affect the other one. So they can both be in there at the same time. They just are there individually and there at the same time. They don't affect each other. So whether A occurs does not affect P of B. So P of B stays the same if you're given information about A. That stays P of B. Whether B occurs or not doesn't affect A. So A given B, given information about B doesn't affect A. So P of A given B equals P of A. The fronts match. And you can do either one of those. It doesn't have to be both that work. You just get 2 results if they're independent. Okay, that's the definition of independence. So, for example, do you live off campus? Select 2 students at random and ask, do you live off campus? The outcomes are independent. Well, first, you want to know why, and it's because they're random. They were randomly selected. Random selection is going to result in the outcomes being independent. So look for that word in some of the problems. It'll tell you how they're related. Suppose 60% of male students live off campus and 60% of female students live off campus. You have independence, gender, and living off campus. Why? 60-40 for the males and 60-40 for the females. So this one's the conditional distribution of living on or off campus, given that they're male, and the one on the right is the conditional distribution of on campus or off campus, given you're female. And those are the same distribution. The conditionals look the same. If the conditionals look the same, they're independent. So that's another way to check if things are independent. Okay, we'll continue this with part 2 next time. Thank you. And I am talking to you today about part 3 of probability rules. And if it's morning where you are, good morning. So we have 3 results that are true if and only if A and B are independent. 3 results that are true if and only if A and B are independent. So the first rule or result is that P of A given B equals P of A. That's the definition of independence. So it means whether B happened or not, here it happened, here it didn't, A stays the same. And you don't have to worry about this reference here. And the second result is that P of A given B equals P of A given not B. So if you had maybe like girls and guys, P of A given girls, here's A, given girls is the same as P of A given guys. So B and not B would be guys, girls and guys. In the previous result, number 1, A given girls would be the same as A for everybody. This is A for everybody. This is A just for girls, let's say. So it's giving you the same result. No matter how you break it down there, those two things are independent. And the last thing is that P of A and B is P of A times P of B, and this is a new result. And mainly you're using it once you know things are independent. It makes it easier to find P of A and B, because remember the multiplication rule is P of A and B is P of A first times P of B given A. But if A and B are independent, this one just becomes P of B by itself. The front one stays the same, the back one goes away. So that would just be P of A times P of B, since they're independent. But to check for independence, you usually use the first result or the second result. The third one you use when you know they're independent. Okay, so how do you use these results? You use them to check and see if A and B are independent. So if any of those are true for your A and B, then they're independent. You don't have to check every one, just any of those. If not, then A and B are dependent, or you can say not independent. So let's take a look at this example. 25% of people read the paper every day. So probability of reading the paper is 0.25. 30% of women read it. That's reading it given or for the women, it's 0.3. And 20% of men read it, so the probability of reading it given male is 0.2. Are gender and reading the paper independent? Well, is reading overall the same as reading for the women? No. So they're not independent. You could have also checked these two, women and men. The readers for the women are more than the readers for the men, so they are not independent. And you could have checked readers compared to readers for the males. They're not equal. You don't have independence. So any of those single pairs of choices there to check would show they're independent. If they're equal, but we don't have equality here, we have inequality, so they're not independent. You can use the results to simplify a problem. If you know you have independence, you can use the result. So they go both directions. So if A and B are independent, then you can say that P of A given B just becomes P of A, and you can go on your way solving the problem. It also means that P of A for the B's is the same as P of A for the not B's. And you can break down P of A and B into P of A times P of B. Now, be very careful. This looks like something that's always true, right? Doesn't it? Because A and B is just A times B, but it's not always true. It's only true if they're independent. How do you know? How do you deal with it if they're not independent? Or if you don't know, you have to do it this way. P of A times P of B given A with the multiplication rule. And if they're independent, then it becomes this starred result. Okay, so it's important to have a list of those around so that you can use it when you're dealing with problems that involve independence. So how do you know they're independent? It'll either say in the problem, or you'll have a random sample. Otherwise, don't assume it's independence. If they have experiments, the results will be independent because they're replicating and doing the exact same thing each time. So the results won't depend on each other, but the experiment would have to state that. Otherwise, it's very important to don't assume independence. Okay, so here's an example. 90% of people age 18 to 28 own an iPad. That should be, get with the 90s, Dr. Rumsey. What is the chance that two randomly chosen people in this age group own an iPad? So this would be the probability of iPad and iPad. There's two of them, right? Because they're independent, it's the exact same probability by itself twice. You can break it up into individual probabilities. Don't need any conditionals. So this would be 0.9 times 0.9 is 81%. And you probably knew that before you started this class. Now, what if you had a ton of events that are happening all at once? If they're dependent, you have to have all these conditional probabilities involved because everybody depends on everybody else. But if they're independent, you can use a multiplication rule and just go P of A times P of B times P of C times P of D times P of E all the way up to Z if you want. So let's look at an example. The chance of a telemarketer getting a positive response, which is a yes, on any given phone call is 0.1. What is the chance that she will get all yeses from 10 randomly placed calls? So they're random, that means they're independent, and there's 10 calls, right? And you need a yes on all of them. So it would be yes on the first one, and a yes on the second one, and a yes on the third one, all the way up to yes on the 10th. Well, because they're independent, you don't have to worry about that the second person depends on the first person and the third person depends on the first and second person, etc. You just say, okay, that's the probability of a yes on the first person times probability of a yes for the second person times probability of yes for the third person times ... probability of yes on the last person, which is 0.10 on each one, which is 0.10 to the 10th power, which is going to be a small value. So that's how you can use the multiplication rule when you have independence and a lot of events happening. There's OR probabilities. That's a union probability. You've seen that before. We have something called the addition rule. When you have the OR situation, you're going to be adding probabilities, not multiplying probabilities. So A or B, first of all, means A or B or both. And it also means the probability of at least one. So if I draw a Venn diagram here, here's the probability of A, here's the probability of B. If I want A or B, I include A, I include B, and I include both. And see how it occurs twice there? So my probability for A or B is P of A by itself plus P of B by itself minus P of A and B because it got counted twice. You take it away one time so it's not double counted. And these formulas are on your formula sheet. The whole bottom half of the formula sheet is probability, and the formula sheet is on Carmen under Course Information module. It's also the probability of at least one happening because you can have one, just A, You can have just B, or you can have both A and B. So at least one means one or more. So if you see a problem that has at least one, you might try P of A or B and see if you can solve it. So why the subtraction here? P of A and B is counted twice in the formula. So you subtract it out one time. All right, let's look at Twitter following example. Suppose 3% of OSU students with Twitter accounts follow Brutus Buckeye. 6% follow President Drake. That should be President Johnson. Now we have a new president. 2% follow both. What percent of OSU students follow at least one? So you can say, oh, it's probability of Brutus Buckeye or President Johnson, right? So this would be P of B, Brutus Buckeye, or which is plus, P of President Johnson, but you counted them twice. So you would have to take away. So you would have to take it away once. So Brutus Buckeye is 3%, President Johnson is 6%, and both is 2%. So this is 0.07. So if you have information about each one separately, and then you have both information about both, then you can use the addition rule there. That's what the addition rule is doing. And I got the cue from the words at least. What percentage of students have an account on at least one of these two social network sites? Twitter, here's all the Twitterers. Here's all the Facebookers. And here's the both. That gets counted twice, so it would be 0.6 plus 0.7 minus 0.4, which is 0.9. And so that's one way to solve the problem. There are multiple ways to solve most problems. Not all problems, but a lot of problems have multiple ways. Now we have a special case. It's called disjoint events. Disjoint events can't happen together. They have no intersection. So the and part is 0. On a Venn diagram, they look like this. How does this affect the addition rule? Well, let's see. P of A or B is supposed to be P of A plus P of B minus P of A and B, right? Well, if P of A and B is 0, this goes away and you just simply sum the two probabilities. That's only if they don't have any intersection. So you can always start with this rule, and then if they turn out to be disjoint means completely separated, then you can use the smaller form of the formula. But one way to do it is just start with the general form and put a 0 here. So you can use this to take a big problem and break it into pieces and then put the pieces together, solve the problem. That's generally how we use the disjoint rule. So what percentage have an account on at least one of these two social networks? Hello students, this is Dr. Rumsey with part 3 of probability rules. As you may have noticed, the end of part 2 is a little abrupt. In fact, I got cut off. So I'm going to go back one slide and start from there. So how do we use disjoint events? They come in handy to break down a problem into smaller pieces that are non-overlapping, and it lets us solve the little problems and therefore solve the bigger problem. So on this example, what percentage of students have an account on at least one of these two social network sites? Remember, one way to do it was to take all the Twitters, all the Facebooks, and then subtract the intersection because that was counted twice. Well, another way to do it is to treat it like three disjoint events. So no Facebook and Twitter, that's 20%. Facebook and Twitter, 40%. Facebook and no Twitter, 30%. And then you just simply add those up to get 0.9. So the trick is to kind of figure out a strategy based on what you're given and what you have for rules to use and what you have for information in the problem. The complement rule is the last rule we have. It's one that you've probably heard of before. The complement of A is denoted with A with a little c as a superscript. And it means everything that is not in A. So if this is set A, then everything out here is A complement. And the complement rule says that P of A complement is 1 minus P of A. So the total probability is 1. You're either in A or you're not in A. So that's why they total to 1, and then you can subtract P of A from each side to get this equation. But where we really use it is not so much to find the probability of A complement, but it's to find the probability of A when we want it. So if probability of A complement is 1 minus probability of A is 1 minus probability of A complement. Why is that so great? Well, suppose this P of A is hard to find, but the probability of the complement is easy. Find the easy one and take 1 minus, and that is a tool you're going to use a lot in here. So really keep that one in your back pocket for when you need it. Sometimes it's easier to think about what you don't want than what you do want. So I'll show you how we'll employ that in a minute here. A telemarketer calls persons A and B at random. Probability of a yes is 0.10. What is the chance of getting no yeses? 0 yeses. No means 0. So it would be probability of a no and a no for A and B, right? Because there's no yeses. So we're going to split that up because they're random, they're independent. So that's probability of no times just the probability of no. And what's the probability of no? If yes is 0.10, no is 1 minus 0.10, which is 0.9. That's the probability of no. So this is 0.9 squared, which is 81. So we use the complement rule there. It's not as exciting as what you'll see in the next example, though. In the next example, it says, what's the chance of getting at least one yes? At least one yes is the probability of one or more yeses, right? Well, what's the opposite of that? If you call 2 people, you're either going to get no yeses, 1 yes, or 2 yeses. You want the chance of getting 1 or more yeses, so you want this. You don't want this. But we just found that one out. It's 81. So this is 1 minus the probability of no yeses, which is 1 minus 81, which is 19. So that's a little bit exciting. It'll get more exciting when we extend this to more than one person, more than 2 people. So the opposite of at least one is none. Okay, the opposite of at least one is none, because at least one on this little number line, and number lines can help. At least one means 1 or 2. What I don't want is 0. The chance of getting 0 yeses was 81, so that's why we subtracted it. So be ready to work problems that use a combination of these rules, and they are the multiplication rule, the addition rule, and the complement rule. And they're all on the formula sheet. So let's make 3 calls and find the chance of getting at most 1 yes. Now what's going on with this? If you're calling 3 people, you can get 0 or 1 or 2 or 3 yeses. And you want at most 1 yes. At the most, you want 1. So that's this and this. Well, if you take the opposite of that, you're finding the probability of 2 or 3 yeses, which isn't any easier than finding the probability of 0 or 1. In fact, it's going to be easier to find 0 or 1 and add them together. Remember, if you find two things that are disjoint, you add their probabilities. So we're going to sum those 2 up. So the probability of at most 1 yes means go all the way up to 1. You don't want 2, you don't want 3. That's the probability of no yeses or exactly 1 yes. So that's the probability of no yeses plus the probability of exactly 1 yes by the addition rule. And those 2 things are disjoint, they're separated, so we just add their probabilities. Let's find the probability of no yeses first. That would be the probability of a no and a no and a no. That's right here. Since they're independent, we can just simply multiply their individual probabilities, P no, P no, P no. 0.9, 0.9, 0.9 is 0.9 cubed, which is 0.729. So that's the probability of no yeses. No yeses just means all no's. Okay, so we got one of them done. We got this one done. Now we need this one. So what's the probability of getting exactly 1 yes? Well, now you have to think about how many ways there are. You could get a yes first, you could get a yes second, or you can get a yes on the third person. And those are different because you're calling different people. And this is just a union probability that you're trying to find. And then you're going to use the addition rule to add their probabilities. Now what this means, this step here, just means there's 3 of these probabilities and they're all the same. Why are they all the same? Well, the yes is 0.1 and the no is 0.9 and the no is 0.9. So it's 0.1, 0.9, 0.9, or 0.9, 0.1, 0.9, or 0.9, 0.9, 0.1, but it's all the same. So it's 0.1, 0.9, 0.9 times 3. 3 ways to do it. And that's 0.243. And you add those 2 together, the no yeses and exactly 1 yes to get that. So that is an addition rule again. Back here, we can throw in that we use the multiplication rule because we split them up into their individual probabilities. So we kind of use a little bit of everything there. So the challenge is to know your rules, know the conditions, know which rule to use when, and note that combinations of rules are often used to solve problems, and different methods are needed depending on what you are given in the problem. And this is the end of the section. Thank you for listening.